Have you ever stopped and wondered how a tiny little sensor, maybe out in the middle of a field, can send a message for miles and then keep on doing that for years on a single battery? Well, today we're going to decode the secret language of LoRa, the amazing wireless technology that makes all of that possible.
So let's start with the big question, the central puzzle. We're all used to a trade-off, right? Wi-Fi gives us awesome speed, but the range is pretty short. Cellular gives us range, but man, does it drain our batteries. So how is it even possible for a tiny battery-powered sensor to send a signal across a whole farm or even a town and keep chugging along for a decade?
Well, the answer is a technology called LoRa. And as you can see here, it just carves out its own little niche. It's not trying to replace your Wi-Fi or your 5G connection, nope. Instead, it's what's called a low-power wide area network, or LPWAN. And it's built for one very specific job, sending tiny little bits of data over huge distances with incredible efficiency.
So what is it that gives LoRa this wireless superpower? How does it go the distance with so little energy? Well, it's not just one single thing. It's actually a combination of 4 really smart design choices. It all starts with just incredible range, and I'm talking up to 15 kilometers. That's over 9 miles if the conditions are right. Now, it does this by focusing on very small amounts of data. Think about sending a single temperature reading, not streaming a video. And that signal, it's highly resistant to interference. But the real game changer, the absolute killer feature, is its ultra-low power consumption. We're talking about battery life measured in years, not hours.
Okay, so how is this possible? The magic here isn't about just shouting louder with more power. It's about speaking a language that's incredibly easy to hear, even when everything around it is noisy. And the secret to that language is a special little signal called a chirp.
LoRa uses a technique called chirp spread spectrum. Now, I know the name sounds a little complex, but the idea behind it is absolutely brilliant. It means a receiver can pick out and actually understand the LoRa signal, even when that signal is weaker than all the background noise around it. It's kind of like hearing a specific whisper from across a really crowded room. This right here is the core secret to LoRa's amazing long-range, low-power performance.
So what exactly is a chirp? Well, it's a radio signal that sweeps its frequency over time. It can go from a low to a high frequency, which we call an up-chirp, or it can go from high to low, a down-chirp. It's this very distinct, predictable sweeping pattern that makes it so darn easy to detect. And this brings us to a fantastic analogy. Think about it. You're in a forest, and it's full of birds, all making noise. Even with all that racket, your brain can easily pick out the specific, rising chirp of one single type of bird. Well, LoRa's radio receiver does the exact same thing. It's trained to listen for that very specific sweeping frequency, and it just ignores all the other radio noise around it.
So how do you take a simple chirp and make it carry actual data? The trick is surprisingly clever. So on the left here, you can see a basic repeating chirp. To send information, LoRa simply changes the starting point of that repeating pattern. Imagine the chirp is like a song playing on a loop. By starting that song at a different point in the loop, you can represent a different number. The receiver just has to listen and figure out where the loop started to read the message. Pretty smart, right?
Now, LoRa isn't just a one-size-fits-all kind of technology. You can actually tune it, kind of like adjusting the dials on an old radio, to perfectly fit what you need to do. There are 3 main dials you can turn. You've got bandwidth, which is how wide of a frequency range the chirp uses. You have coding rate, which adds a little extra data to help correct any errors. But the most important one, the one you really need to understand to get LoRa's magic, is the spreading factor, or SF. This determines how much data gets packed into each chirp, and it's the key to the ultimate trade-off, range versus speed. And that brings us right to the fundamental trade-off that is at the very heart of LoRa. You have a choice. You can send your data faster, or you can send it farther, but you can't have both. This spectrogram really shows us what the spreading factor is actually doing. On the left, a low spreading factor gives you these fast, steep chirps. But as you crank up the spreading factor, like SF12 over on the right, the chirp gets stretched out over a longer period of time. This longer, slower, more deliberate chirp is like a bird singing a very long, clear note. It's just much, much easier for the receiver to pick out from the background noise, and that's what gives it that incredible range.
And what this formula shows us is the cost of that extra range. Now don't worry, no math quits here. All this really says is that as the spreading factor, or SF, goes up, the time it takes to send just one single chirp goes up exponentially. So to make the signal easier to hear from far, far away, you have to send it much more slowly. The price of range is always time.
So let's just summarize that whole trade-off. A low spreading factor, something like SF7, gets you a higher data rate, it takes less time to transmit, but you get a shorter range. A high spreading factor, like SF12, gives you that incredible long range and it's way more robust to noise, but it comes at the cost of a much, much lower data rate. You just pick the setting based on what you need.
Okay, so enough theory, right? Now that we get the trade-offs, let's see how this actually works out in the real world with the simple, practical example. So, picture this. A farmer wants to check the soil moisture in a field that's maybe a couple of kilometers away from the main farmhouse. There's no Wi-Fi out there, and you're not going to run cables that far. This is a perfect job for LoRa. And here's the hardware that makes it happen. Out in the field, you've got a simple little board with a LoRa chip, and it's hooked up to a moisture sensor. Back at the house, a second LoRa board is set up to be the receiver. There's no complex network, no router, just a direct point-to-point radio link.
So the process is pretty straightforward. The sender, board out in the field, wakes up for a second and reads the moisture level. Now, to make sure only the right receiver is listening, it adds something called a sync word. Think of it like a digital password or a secret handshake. It then encodes the data into a LoRa packet and just chirps it out into the air. Back at the house, the receiver is listening only for that specific password. When it hears it, it decodes the chirp, and boom, the farmer gets their data. It's simple, it's robust, and it's incredibly efficient.
So when you really boil it all down, LoRa's superpower is this unique combination of extreme range and extreme endurance, something that really no other mainstream wireless technology can offer.
All right, let's recap the most important points here. First, LoRa gets its amazing range by using those distinctive chirps that can be heard even when they're quieter than the noise around them. Second, the spreading factor is that magic dial you can turn to trade speed for more range. And finally, all of this makes it absolutely perfect for connecting simple, battery-powered devices in places where Wi-Fi and power outlets just don't exist.
And that kind of leaves us with a final thought. We've really just scratched the surface of what's possible here. As we continue to connect our physical world to the internet, placing tiny sensors in our cities, on our farms, and throughout our environment, what new applications, what new insights and efficiencies will technology like this make possible? The secret language of the chirp is really only beginning to be spoken.